Welcome everyone to our Thursday afternoon seminar. Our speaker today is Son Mi from the University of Graz. He will tell us about composite dark matter.
Sure. Thank you for the introduction, Savas. And thank you, Enrique, also for allowing me to come and speak about my work. Yeah, so my name is Sean Mi. I'm originally from Ireland, but I work and live in Graz in Austria. So most of what I present today is actually from a work in preparation with my collaborators. So we're actually split across the University of Graz and the University of Vienna. So just before I begin, I'm going to provide a little outline of my talk today. So I'm not sure it's very necessary, but I'll provide a very, very brief introduction to what dark matter is. I'm not sure exactly how many people here are familiar or work on it, but it's always useful to have some small introduction. I'm going to introduce some candidate models for particle DM, and in particular, I'm going to introduce the idea of strongly interacting DM. I'm going to describe the spectrum and the symmetries of sp4 gauge theory in terms of its low energy phase, right? So in particular, the pseudo-Nambu-Goldstone bosons that come from chiral symmetry breaking, and this spin 1 multiplet, so the analog of the row mesons of QCD. I'm going to describe how we can minimally couple this dark sector to the standard model and describe all the associated explicit symmetry breaking patterns. And finally, I'll provide some outlook and conclusions. So the group, we're called the Strong DM group. We have a focus on, as you can imagine, strongly interacting theories, which could describe the dark matter. We take several different approaches in characterizing SIMP, or strongly interacting massive particle dark matter, and I'll explain a little bit more about what that means. And finally, the sort of the main idea behind our group is this close collaboration between people from different disciplines. So in particular, we have cosmologists, lattice theorists, phenomenologists, and even experimentalists all working on the same project. Okay. Dark matter is probably something which needs not much of an introduction, but it's one of the biggest unanswered questions in physics today. There's evidence on a variety of scales. So I've included 2 examples here. One is the classic galactic rotation curve. Rather than falling off as 1 over the square root of r, the orbital velocity remains approximately constant. And also data from bullet clusters, so the spatial offset of these mass peaks indicates that there's some mass present that we can't see. Well, as a particle, what are the characteristics we expect the dark matter to have? Well, one is that we expect it to be stable, or at least very long-lived, with lifetimes comparable to the age of the universe. We expect it to be weakly charged under the standard model. And what I mean by this is, well, the reason I say this is just to make it clear that when I talk about strong interactions, I'm talking about strong interactions within a hidden sector, not strong interactions with the rest of the standard model. It's going to be mostly non-relativistic, or as we say, cold, at the time of matter radiation equality. And finally, this might be a contentious statement, but probably not a standard model particle. So neutrinos were the sort of natural candidate initially, but they've been since ruled out. I think there are still some candidates that exist even within the standard model that haven't been ruled out, like hypothetical sextaquark states, I think. Some people talk about this. Not an expert on that, but we believe it's probably not standard model particle. Okay, so what are some candidate theories which could describe dark matter as a particle? So for a long time, the standard description was in terms of the WIMP, or weakly interacting massive particle, right? So here, dark matter is a thermal relic. At some point in the far past, it's in equilibrium with the thermal bath. And it, as we say, freezes out through an incomplete annihilation process. So we can imagine that we have this process as well as the inverse. At some point, dark matter production falls out of equilibrium and the dark matter starts to annihilate until the point where dark matter can no longer efficiently find other dark matter particles. And then we say that the process freezes out and the abundance remains approximately constant. So weakly interacting particles at the weak scale. So if you look at this, of what I have here, in order to get the observed relic density of about 0.1, we need alpha about 0.01 and dark matter at the 100 GeV or so scale. Right, so at the time, this was called the WIMP miracle, which is a bit of hyperbole, I think, because it's really just a coincidence. But anyway, this was for a long time the standard description. But in more recent years, there have been descriptions of alternative routes to get to the relic density, right? So it was found that if we posit dark matter, which has this sort of 3-to-2 cannibalization process, then if this is the primary number changing process, then you can reproduce the relic density for an alpha around 1 and a freeze out time x. So this is the dimensionless freeze out time, which I'll. Is there some chalk handy? Yeah. We mind just defining it. So that's not confusing. So where x is the dimensionless time parameter. Hopefully you can see this. So it's mdn over t. Okay. So this was dubbed the SYMP miracle, and I'll explain exactly what that means in just a second. But this is the kind of defining characteristic of the SYMP paradigm, right? That we have this 3-to-2 cannibalization process rather than this 2-to-2 dark matter annihilation. Yeah. Well, the 3-to-2 is kind of so you're asking if you could instead have like just a 2-to-1 annihilation or something like this. That's probably possible, but it's not really a characteristic of the type of theories that we're going to talk about here today. But yeah, it's a good point. I think the motivation behind the 3-to-2 is that it occurs naturally in these sort of strongly interacting type theories rather than it being the simplest description, right? So yeah, you're completely right. But for these sorts of theories, you get this for free. That's the reason that it's a 3-to-2. Yeah, so in the standard model, exactly these sorts of interactions are sourced by the so-called Bess-Sumino-Witten term in the action for QCD. So in particular, there is a observed K plus K minus, I think, to pi 0, pi plus, pi minus. Anyway, so in QCD, these sorts of interactions you get for free because of this term in the action, this topological term. So this has sort of spurred a new interest in dark matter as a composite particle in a QCD-like hidden sector. So just like in QCD, we have a dark sector which has some matter content, and below some like this, right? Right. Stable particles make good dark matter candidates. So, okay. So why do we consider strongly interacting DM? What are the sort of nice properties that theories like this have? Well, one, the stability of the DM in isolation is guaranteed, right? It just has nothing to decay to. Secondly, we get self-interactions of this form, right? 2-to-2 scattering and 3-to-2 scattering. So this 3-to-2 is nice because it allows the dark matter to freeze out in isolation, as well as this sort of 2-to-2 self-interaction, which is useful for explaining some fine structure or fine-tuning problems, I guess, in cosmology. I think this helps to explain the core cusp disparity, or it can. Okay, and I've provided here a plot of the parameter space which reproduces the relic density. Okay, so just a little review of strong dynamics in the standard model. If we look first at the UV level, we have this scale at which the strong coupling diverges and quarks confine into color neutral combinations. So pions here are sourced by bilinears of this one, QQ bar. But they can also be characterized as the so-called pseudo Nambu-Goldstone bosons of chiral symmetry breaking. Right? So by chiral symmetry, I mean this symmetry here. So SUNF cross SUNF, a global symmetry which separately transforms left and right-handed components of quark fields. But this is spontaneously broken by the quark condensate, and actually also explicitly broken by quark masses. Right? So that's why we call them pseudo Nambu-Goldstones, because they're not exact massless Goldstones. They have a mass, which we can see as sort of perturbations due to the quark masses. So we can see that after the symmetry breaking, we end up with NF squared minus 1 PNGPs, which is just the dimension of this group. Okay, well, what are the methods that we use to study the PNGPs? Well, there's a couple of things that we could think about. One is lattice field theory, which I'm not going to talk too much about today. But this is a non-perturbative description, simulates the full theory, and allows us to access the low energy constants of our theory. So I guess in particular, I mean pion masses and decay constants, but really you can access all of the low energy constants of your theory through this method. With the caveat that this is very costly, especially that if we want to work anywhere close to the chiral limit. Yes. Oh, sorry, I thought I heard an interruption. Okay, the second method we use is chiral perturbation theory. Before anyone comments on it, I'm not crediting this to Georgi, I'm just providing a reference. I had a comment on this the other day. So this is a general and systematic expansion in the small momenta and masses of our PNGPs. Right? So we construct a theory which is completely consistent with the symmetries of the UV Lagrangian, but it's not now perturbative in any gauge coupling or anything like this, but in the momenta and the masses of our PNGPs. So this is really a description which is valid only in the chiral limit when the quark masses are small, but in principle, we can just integrate out heavier flavors, and their influence can then be seen in the low energy constants with each term in the expansion. So a problem arises when we want to go beyond leading order in chiral perturbation theory, because here the LECs, the prefactors for each term, require some extra input. So for QCD, this has come both from experiment and from the lattice. We don't have the luxury of fixing them through experiment, right? Just lattice field theory, and these are very, very costly to compute. But I'll talk a little more about that later. So one thing I want to pay a little bit of lip service to before I move on is just this question of scales. So as I said, chi-pt is only precise in the chiral limit where the mass of our quarks are very small compared to the characteristic scale of the theory. Right? So here, the interpretation of pions or whatever, right, as PNGPs is good, right? And here it makes sense to consider leading order chiral perturbation theory. But one thing we want to make clear is that, well, if we stray a little further away from chirality, then this interpretation becomes less reliable. And we need to have some way of understanding exactly how reliable it is. So this is something we're thinking about as well. I'll point out some of the ways that it fails later on. And finally, I just want to mention that if the quarks exceed the scale of confinement, if they're much larger, then you need some other approach to describe them. Right? So in particular, heavy quark theory. Okay. My group doesn't mostly consider SU3 as a gauge theory, though. We're in particular focused on SP4, and I'll explain why that is. So if we look at the table here, for each of the two gauge symmetries, right, I've written the corresponding flavor symmetry and what it's broken to by the condensate. So if we look at the multiplicity of Goldstones that we expect in each class of theory, we can see that, we can see that they differ, right? So as I say here, the non-vanishing 5 Goldstone vertex that I wrote down, so this 3-to-2 process, for this to exist, you need at least 5 distinct Goldstone bosons, right? So if SU3 is our gauge theory, then the most minimal realization we can have is for 3 flavors, right? It's just a consequence of looking at this. What you might notice is that a more minimal realization is possible if we consider fermions in pseudo-real representations, right? So for SPNC, for NF equals 2, we already have 5 Goldstones, right? So already this 5 Goldstone vertex is possible for a smaller number of flavors. SP4, I have the defining property of it a little bit later. I'll just stick to it now. Right, so the defining property of the symplectic group is that it's the subgroup. So I should just say that, so I write this property here, but it's, so it's the subgroup of SP of SU2N, which has this property, right? So it's the subgroup of SU2N, which has this property here, right? So this is the symplectic group, right? So I'll explain a little bit why that results in a different spectrum in a second. The symplectic group is only defined for even, so it has to be even.
As a consequence, you are going always to end up with basically the double of Goldstone. The number of Goldstones that you are at the end talking about, yes, is close to the double of.
Yeah, that's true. Yeah, so in the large end limit, yes. Yes, exactly right. So yes, exactly right. Okay. Yes, so as I said, for a smaller number of fermions, we can actually arrive now at a non-vanishing 5 Goldstone vertex. So this is kind of what motivates us to look at symplectic groups. It's that you have this more minimal realization. For a smaller number of fermions, you can still have this interaction possible. Okay, so yes, as I say, we consider the fundamental representation of this before. So what do I mean when I say pseudo-real representations? Well, I'll explain. Pseudo-real representations are defined by the fact that they are isomorphic to their conjugate representations. So, as I said, this is the defining property of the symplectic group, which at the generator level implies exactly what we're looking for. Right? So, in particular, this means that we have symmetry between particle and antiparticle, and an overall expanded flavor symmetry. Right? So I'll explain what this expanded flavor space looks like in just a moment. But first, I'll highlight the difference between pseudo-real and complex representations in terms of global symmetries. So I guess this right-hand side should be familiar to most people. But if not, all that this says is that, okay, when we write down our action for 2 fermions in a complex representation, that we have this global U2 cross U2, which is broken to this subgroup by the axial anomaly, and finally to SU2 cross U1 by chiral symmetry breaking, so what I wrote before. Right? So in particular, we get, so how many generators here? 7 minus 4, 3 total Goldstone bosons for complex fermions. Which, if we have non-degenerate masses, is broken down to just a U1 cross U1. For pseudo-real representations, we have this expanded global symmetry, a U4 broken to an SU4, which is broken to SU4 by chiral symmetry breaking. And even for the case of non-degenerate fermions, we actually retain this expanded SU2 cross SU2 global symmetry. So if we want to look exactly what this flavor space looks like, our flavor space is actually 4-dimensional for one, and it involves symmetry between these 4 Weyl fermions, right? So we have an SU2 symmetry, which rotates these 4 spinors into each other, right? So here, S is the same matrix in color space that I wrote earlier. And yeah, these are the left and right-handed components of our Dirac spinners, if you like. Okay, so as I said, our global symmetry is expanded to SE4, and the condensate breaks this down to SP4. So the dimension of SE4, or well, the number of generators is 15, minus 10 from SP4 gives you 5 PMGBs, which is exactly what we wanted. Okay, well, what does the spectrum of this theory look like? Well, for one, the theory contains all the standard mesonic states of QCD, right? So all our pions are row mesons. They're all contained in this theory. But because of the expanded symmetry, we get also these extra states, well, we can call them mesonic, but I'll define exactly what they are in a moment. But we get these extra states in the spectrum. So I say here the theory contains no baryons, which is maybe some people would disagree, but it's a semantic disagreement. When I say no baryons, I mean there are no 3-quark bound states, right? There's no way of forming color neutral combinations of 3 quarks.
The chiral group is lost indeed, in other words. Are the quarks still rotating at the left and right and before?
It's actually a subgroup. So if you like, this SE2 cross SE2 is a subgroup of this SE4, right? So it's still there, but it's just expanded. So it might be a little, so some people still call this chiral symmetry breaking. It might be a little bit wrong to do that because it kind of mixes this expanded flavor symmetry with this chiral symmetry as well. Right? Yes, so as I said, the theory doesn't contain any bound states of 3 quarks, so no baryons. And so in what follows, I'm going to just first consider the case of degenerate fermions, right? So that our up and down quarks have equal mass. In particular, what we have in our spectrum now is diquarks, right? So we can't really form color neutral combinations of 3 quarks, but color neutral combinations of 2 quarks or anti-quarks are possible. And in fact, because of the expanded flavor symmetry, these actually form part of the Goldstone multiplet. So these are, as long as we don't have any source of explicit breaking, apart from degenerate white masses, these are actually completely degenerate with the other guys, right? So along with our standard URD states, we also have states of this one. So diagrammatically, this is what the multiplet structure looks like. Rather than just our pi 0, pi plus, pi minus, we have a 5-plet of degenerate Goldstone bosons, which split into a 4+1 when we have non-degenerate fermions. Our rows get expanded even more, right? We actually have now 10 spin 1 mesonic states in our spectrum, right? Which are completely degenerate until we turn on non-degenerate quark masses, and then they split into a 4+6. Okay, so I'm going to describe exactly how we construct the chiral Lagrangian for this sort of theory. So I'm not sure exactly how familiar people are with chiral perturbation theory, but it's really the exact principles I was describing before, right? So
can I ask a question before you do this? Sorry.
In terms of, is there something I'm losing?
I have a question. I'm a little confused before you go into the chiral Lagrangian. Is that okay?
Yeah.
Can you? So yeah. I'm a little confused about whether you have both a color interaction that binds these quarks and a flavor symmetry.
Okay. Don't think so. No. Yeah, this would be a good idea. Yeah. Okay. Well, I can't actually look at the chat, but if you could write it in the chat, whatever your question is, that would be great. And then someone can tell me.
Can somebody who is there just repeat the question to him?
I think Belen is asking.
No, it's Greenstein who is asking. If
Yeah, I'm asking a question. I'm just confused about what is the gauge symmetry? What is the strong interaction that's binding these things? And what is the flavor? I mean, if you have an SU3 color, and in addition, you've expanded the flavor symmetry by putting additional quarks into the system, then I have no idea why you have no baryons, and I would like an explanation of that. On the other hand, if what you're changing is the gauge group from SU3 to SP4, then you shouldn't be calling it flavor because it's confusing, but now I understand better what's going on.
wow.
Sure.
Did you hear it or should he write it? I heard it.
It's very low when he speaks. We cannot hear them.
Ben, can you
Yeah.
write it in the chat? Can
All
you
right.
write it?
All right.
Yeah, that would be best.
He's writing in the chat.
Write it in the chat.
Sure.
Okay.
It's coming from.
Yeah,
Okay.
I can do that. Or-
The problem is that if you want to keep it close out of the laptop, and exactly what I was doing here, and
Yeah,
then
feedback.
the micros pick it up.
Yeah, there is feedback.
Yeah,
There is feedback.
Well, I told them to write the question in the chat.
that would be probably easiest.
He must be writing. He's wondering about flavor versus color versus confinement of the color forms.
Well, I think continue and if
Yeah,
they write
sure.
it at some point.
Okay. Yeah, sure. If the question is written in the chat, I'm happy to answer it. But, I can't quite hear it right now, so I'll continue.
What I don't understand is because some of the audience doesn't listen to this. Okay, because they don't have.
Here it goes. What is the strong interaction? What is the strong interaction that is binding the parts? If it is color, is the free way there are no values.
Okay, I think that I maybe should be more
No, no.
clear. There,
You
yes.
should repeat the question so they can
Yes,
hear
sure.
it.
And the
So the
second
question
part,
is, what is
and the
strong
second part
interaction
of the
between
question.
If it is color SU3, why are there no baryons? If you have made color an SP4, then please don't call it flavor. There are two symmetries. Maybe I should make that even more clear. There are two symmetries going on here, right? We have an SP4 gauge symmetry and an SP4 flavor symmetry, right? So they're two different things. This is the local symmetry, which binds the quarks. This is the flavor symmetry that results from just the group structure. Okay, I should have made that clear. Yes, excuse me. Sorry about that. So yes, that's exactly what I'm talking about, right? So we have local SP4, which binds the quarks, and the global SP4, which is the remaining flavor symmetry of the theory after chiral symmetry breaking. So I'm sorry I didn't make that clear. Hopefully that makes it more clear, right?
He said okay in the chat.
Hopefully it's satisfactory. Yeah. So we describe the dynamics of our PNGVs through fluctuations in the orientation of the vacuum condensate. So it's we apply transformations on the vacuum of the coset SU4 over SP4, which gives us this field here. And we build our chiral Lagrangian out of this chiral field. Okay. Transpose, right? This is a matrix. So if you like, what we have here is like, so our pions are like this, right? So we've got 5 Goldstones, so A goes from 1 to 5. So we build a matrix out of this, and that's exactly what this guy is, right? Yeah. And this E, I don't think I defined either, but this E is actually just, so for 2 flavors, it's this, right? It's our symplectic invariant in flavor space, right? So the S I defined before, S is what we would call it in color space, E is just the equivalent matrix in flavor space. Okay, So at leading order, the chiral Lagrangian takes this form, right? It's just the most general order p squared terms that we can write down. It's actually been pointed out to me though that this is not a unique form for the mass term of this sort of theory. In general, you could have terms proportional to m squared as well, but that's not something I'm so familiar with anyway, right? Assuming that our power counting is correct, that our response in terms of quark masses is linear, then this is the correct form of the mass term. Right. So you can see that this is going to give our Goldstones, our pions, a linear dependence on the quark masses. So in particular, it looks like the square of the pion masses goes like Q over squared. It has this dependence on the quark masses. This is called the Gelman-Oaks-Renn relation. But assuming that this is the correct leading order description of the pion masses, then this is the correct one. Okay, so that theory is one which describes just interactions amongst our Goldstones. But what we want to do is look at all the interesting composite states in our hidden sector, right? So one possibility then is the spin 1 multiplet, and so completely analogous to the row multiplet in QCD, because this can play an important role at colliders and elsewhere. And to include these in the effective theory, we make use of this idea of hidden local symmetry. Okay? So what this means is we introduce them as dynamical objects, which couple to the pions as gauge bosons of a spontaneously broken hidden symmetry, right? So we stress it's not a fundamental gauge symmetry, it's just a method of introducing these guys as dynamical objects, right? Okay, so the idea then is that we gauge a copy of our global SP4. So now we have this other local SP4, which we just break completely with the condensate, right? So now in our theory, additionally, we get 15 actual Nambu-Goldstone bosons, which are massless. And these guys are going to provide mass to all our spin 1 states. Right? So just completely analogous to the Higgs mechanism. So this is what our two sectors, our two symmetries look like. So we have our global SQ4 flavor. Maybe I have written here. So excuse me, I've written global SQ4. In principle, we can gauge the total SU4 symmetry and then include our axial vectors as well. Right? But this is the idea. So we have a global SU4 as well as a local SU4, which we break with a non-vanishing vacuum expectation value of sigma and then this scalar field S. So that breaks our symmetry down to just a global SP4. And now we have additional Nambu-Goldstone states in our spectrum, and these provide masses to all our vector states, right? So some of our collaborators in this paper here actually have fixed the masses of the vector and axial vector states completely in terms of low energy constants of this full SU4 cross SU4 theory. But for us, we just keep this as a free parameter, right? So the row mass in comparison with the pion mass is for us just a free parameter. Okay, so what are the things now that characterize our low energy states? Well, the scales of our full UV theory. So for example, the chiral condensate, the quark masses, and the confinement scale. These are going to be encoded in our low energy constants in the EFT, right? So the masses of our particles as well as their decay constants. So for degenerate fermions, lattice computations are already available. And some bits have been provided, right? So this is actually, again, from some of our collaborators. So what do we think about next? Well, so far we've described a hidden sector which exists in complete isolation from the standard model. So what we might think about next is, well, if we want to actually look at this theory, we need to introduce some simple portal, which allows the model to talk to the standard model in some way. So the most kind of natural, I guess, or simple extension is just a U1 field, right? So some of you might be familiar with this idea of a dark photon, right? So this is we extend our theory with this U1 symmetry, under which all our dark quarks are charged. Some dark Higgs mechanism breaks this symmetry. And finally, we allow our dark photon to talk to the standard model weak hypercharge through this kinetic mixing, right? So what this results in is that we have dark matter, which is so-called newly charged under the standard model group, right? So we have now charges which are controlled by this small parameter epsilon, right? So this is sort of one of the advantages as well of this 3-to-2 type interaction I was talking about. So I'll just quickly show you what I mean. One thing you might notice about this 3-to-2 interaction is that it's going to ensure that the dark matter heats up relative to the standard model, right? This is going to ensure you have 3. If all your states are degenerate, you have 3 in the initial state and 2 in the final state. So for one, introducing this sort of portal allows you to dump heat into the standard model, basically, right? But now you have 2 processes which are totally separate, right? So if you noticed for the WIMP miracle or the WIMP model, right? When you introduce this sort of portal, this annihilation, you also get these scattering processes. So, but now they're controlled by the same parameter. So you now have constraints coming both from these sorts of interactions and these. But here you have the 2 things decoupled, right? So this comes from the strong dynamics and this comes from this U1 extension. So it's kind of nice that it decouples self interactions from.
Can you have interactions among 5 Goldstone? 3 of them are dark matter and the other 2 not? In other words, can you annihilate the dark matter into something which is not dark matter?
No, these would be dark matter as well. So
everything dark matter in the 5 going to the surface?
Yes. Yeah.
So the model does not contain other 5 interactions among Goldstone.
Maybe I misunderstand your question.
No,
Do you mind?
the question is, you are precisely building an approach to the issue such that you can get interactions among 5 dark matter particles.
Yeah.
And these are the new Goldstone.
Yes.
The new Goldstone sets. They belong to the new Goldstone set.
Yes.
My question is, can you generate in the same context also interactions among 5 Goldstone bosons which are not only dark matter, I mean, that share dark matter and normal?
Oh, I think yes. Yeah, because what makes the reason we consider them dark matter is 1, they're degenerate, and 2, they're all stable, right? But if you have 2 which are not stable,
can you produce from the standard Goldstone boson 2, 1, at the end 3 dark matter?
Okay. So you're asking if you can have like a 2 to 3. Yeah, this is present, but the idea is that in the early universe, both of these are present and they should be in equilibrium. But at some point, as the universe cools, this will become dominant.
I wonder if the fact that all the channels are open are possible. If you are going to use the third one, that means annihilation of 3 into 2, you move into the process the other way around, and then you produce with the same probability the other cross channel.
Sure, but well, the idea is that as the universe cools, this one becomes kinematically suppressed, right, and this one doesn't. Yes, that's really the point. So you're right. Both. Yes, well, they in principle can be. That's a consequence of the kinds of work masses you're considering. But yeah, You're correct, but yeah, at some point this one becomes preferred over this one, right? It's just a consequence of kinematics.
So the what range of masses are we talking about?
Hundreds of MeV.
Hundreds of MeV.
Mm-hmm. Yeah. So that's kind of the mass range that's suggested by these sorts of models. Yes. Okay. So as I've said, so this is the sort of relevant interaction at colliders, right? So
But can I ask you
yeah.
something? So you're saying that the relic density essentially comes from the 3 to 2.
Yeah.
But now that you're putting this dark photon,
yeah,
how
it's a good question. Yeah, it's a good question. So that depends on the strength with which it couples. Mm-hmm. Yeah, it's a good question. So you're right. So I introduced this as the primary number changing process, but once you introduce a dark photon and you have something like into standard model stuff. The idea is that this is controlled by this small parameter epsilon. If epsilon is not that small, then yeah, this will become significant. And there are actually some papers on exactly this. So once you have this portal with the standard model, how small does epsilon have to be to ensure that the 3 to 2 is the primary number changing process and not this? It's around 10 to the minus 3 or 10 to the minus 4. If it's that significant, then this becomes a significant player in relative density computations. But if it's sufficiently small, then we see that the 3 to 2 still dominates. But you're right? This sort of coupling introduces a couple of different ways you can get to the relative density. But provided epsilon is less than, I don't know, 10 to the minus 4, it's pretty safe that the 3 to 2 is still dominant. Okay. So after electroweak symmetry breaking, this V is going to mix with our standard model photon and our Z, right? If this dark photon is very light, then it's going to dominantly couple to the electromagnetic current. If it's a little heavier, then mixing with Z becomes significant and you can't really ignore it, right? Yeah, no worries. No worries.
The coupling with that photon is not making your dark matter unstable.
No, so I'll explain why. It could, in principle, it could. Yeah, that's a good question too, and it's another nice property of these sorts of symplectic gauge theories. Right? So in general, if we had just an SU2 symmetry, you always have one guy which is unstable. You can't avoid it, or an SU3 gauge symmetry, excuse me. So fermions in complex representation, you will have one guy which would be unstable. But for this sort of theory, no, and that's what I'm going to show you. So yeah, you're right to say that in the presence of these sorts of couplings, right, we actually add a source of explicit symmetry breaking to our theory, right? So we know that the symmetry breaking in the effective theory should match that of the UV Lagrangian, which can have important implications for the stability of the DM. So you're very good to point it out, but I'll show you why it's not the case for this theory. So symmetry breaking is sourced by terms like this in our UV Lagrangian, where now, yeah, this is the 4-component vector of Weyl spinors that I introduced earlier, and Q is a charge matrix in flavour space. Okay, so now we can work out the considered symmetry by performing a flavour rotation, which I'll just skip to this table, which kind of outlines what I'm talking about. So you're right, there are many choices or charge assignments which break SP4 maximally down to this U1 cross U1. And here we at least have one unstable guy, right? So the analog of the pi 0, that's going to be unstable. But interestingly, there are charge assignments which we preserve this like non-trivial part of the flavour symmetry. And here we actually have a multiplet structure where everything is protected, right? So if you like, what you can see this as is that we have 2 guys which are protected by their U1 charge, and 3 guys which are protected because they transform in the adjoint of the SU2, right? So they still have some conserved quantum numbers which protect them, even in the presence of a non-trivial charge assignment, right? So that's kind of another interesting aspect of this theory, is that you can have dark matter which talks to the standard model through this sort of portal and still protect it, which isn't true for standard SU3, as I say, right? Non-trivial assignments can still completely stabilize the DM. We don't need any sort of external stabilizing symmetry. Okay, so I'll talk about some of the decays that we can still see in our hidden sector. So what we can think of is that our DM component is still completely stable, but some of the heavier states can in principle decay, right? So if our rho is made a singlet, then it's going to be able to mix with our U1 field in some sort of interaction like this, right? So if, and this is a big if, M rho, so the mass of the rho satisfies this condition, that it's less than twice the mass of the prime, then the rho should decay democratically to standard model FFY. If this isn't the case, then the rho is going to decay dominantly back into the hidden sector, which fine, you know, there are still other signals we can look for. So in principle, if the rho decays in this way, then we can observe processes like this. So standard model quarks annihilate into our Z prime or dark photon, whatever you like, and produce a pair of dark quarks. These guys hadronize and produce some number of final states. Most of these are going to be either stable or they're going to decay back to dark sector stuff, right? But if we have one singlet, which mixes through something like this, then it's going to be able to decay back to standard model stuff and produce a visible jet. So this is sort of a process which is characterized by semi-visible jets. Now, even if that's not present, we just have some missing energy, and that's also a nice signal. It's not as nice as this sort of monochromatic line, but still. Unfortunately, modeling these sorts of theories is kind of limited at the moment by event generators, which are pretty SU3 specific, unfortunately. But anyway. So one of the things I also want to quickly mention is, well, how does this symmetry breaking that I mentioned before become manifest in the effective theory? Well, symmetry breaking amongst our Goldstones, right? They're not unstable, but they still split into a 3 and a 2. How does this become manifest? Well, we have mass splitting due to the gauge couplings. In the EFT, the symmetry breaking is sourced by this sort of term in the action. And we decided to compute, or at least estimate, this mass splitting through one loop contributions to the self-energy. So these guys here, right? Where we make it clear that these empty dots indicate that all the contributions of order E dark squared must be accounted for. So in general, that means that these don't just include direct coupling between Goldstones and the dark photon, but also with the rho. And under the assumption of vector meson dominance, we arrive at this expression for the mass correction due to U1 charges at leading order in chiral perturbation theory. Okay, so well, one nice thing is that we have now different symmetry breaking properties than mass splitting due to non-degenerate quarks, right? So we can still have fine splitting amongst our Goldstones while preserving exactly the stability of the DM. And just to make it clear what I mean by this, I'm going to scroll back to, sorry, this guy here. So what you should notice is after we break the degeneracy between quarks, we always have a singlet, right? So as soon as we couple now a dark photon, this will decay, right? So we can't have both of these at once, is basically what I'm saying. So, but by just looking at mass corrections due to gauge couplings, we can still have some splitting amongst our Goldstones, which could be interesting cosmologically. Okay, so I'll very just quickly run through the other sorts of explicit breaking that our group considers, which is, as I said, fermion mass splitting. So for non-degenerate fermions, our global sp4 breaks to an SU2 plus SU2, one for each flavor. And this means that our PNGBs always transform in a fourplet and a singlet of the remaining symmetry. So this means we should have now mass splitting between the flavor singlet and then the off-diagonal fourplet. Right? And this is kind of where when we run into sort of a limitation of leading order chi-PT, right? The GMOR relation, which is the leading order relation which describes the pion masses. I think I got rid of it, but this predicts a totally degenerate spectrum, right? In fact, it should be kind of clear to see why that is, because mass splitting amongst these guys is going to have to depend on the square of the difference between up and down quarks, right? If that weren't the case, then you could just relabel up and down and, you know, flip the hierarchy, which makes no sense. Right? So it has to be order NP squared. That means you need to understand next to leading order chiral perturbation theory. In particular, for our theory, at order n or order p to the 4, we get these mass terms, where the form is definite, but these low energy constants, A4, A5, etc., these are not known, unfortunately. We don't have the luxury also of fixing them from experiment. So this is probably going to be a task for the lattice. But anyway, one thing we're thinking about is, okay, well, we have now this bunch of constants, which ones are the most important to us for calculations, and then we can maybe decide, okay, we want the lattice to compute these first. But yeah, anyway, as I say, corrections to the masses and decay constants can now be expressed in terms of these order p to the 4 low energy constants. On the lattice, however, in the full theory, you can compute these masses and decay constants already. And so here's some preliminary results from our group as well, which show exactly how this mass splitting occurs. So this is from lattice proceedings from some of our collaborators, but we also have a work in preparation, which includes more results to this. So we have these fits of the masses of the various meson states as a function of the flavored vector mass. For us, this is really just a proxy for the mass splitting itself. It just produces nicer plots. That's the only reason it's there. But some interesting aspects that we already see is that for large enough mass splitting, we have this inversion in the hierarchy of masses of our off-diagonal pions and our flavor diagonal row, right? Which is quite interesting, I think, right? So it kind of at least establishes a regime where you can justify that this is a theory of pseudo-Nambu-Goldstone bosons. Clearly, once you go beyond this point, it definitely is not. Probably you have to stay quite close to here. But okay. So just to provide some conclusions, well, dark matter remains one of the most important unanswered questions in physics today. And as I hopefully have shown, strongly interacting theories can naturally explain some of these properties we expect. We've looked at the minimal realization of the SIMP scenario and constructed the low energy theory of this SU4 to SP4 global symmetry breaking. We've coupled the lightest spin-1 states to our PNGBs through the use of a hidden local symmetry. We've coupled it also to a simple U1 mediator and described completely the associated symmetry breaking patterns. And finally, we've looked at the decays of hidden sector particles and the associated consequences. So what we're working on next is building a fine rules model which describes our theory. And from that, we should be able to look at some decay widths, cross sections, and start constraining our parameter space. So that's everything I have for you today. Thank you for listening.
Any questions? Comments? We already had many questions. There are any more? Okay, I have a very quick question. So for these kinds of dark matter models that you mentioned, are there any smoothing down signatures that you could see, for example, in cosmology? Could it be these dark photons you mentioned? Or...
Yeah, well, the smoking gun really is, well, But what we've been thinking about at colliders is really this, right? This is, it should be a suppressed process, but at the same time, it's going to give you like a monochromatic line. It's as smoking gun as it gets. But if that's not the case, then there are still other things you could look for. For example, this sort of theory is also going to contain a light pseudoscalar singlet, like the eta, right? This is never protected, no matter the charge assignment. And in principle, this could be long enough lived that you could look for decays of this, right? So this is another possible signature. But again, we haven't thought so much about the eta just yet.
Cosmology, would you expect anything unique? As I said, these dark photons maybe? So if I see some dark photons like at the early universe, would that be a hint for this kind of models?
Don't you get a contribution to an effect from the dark photon?
Oh, sure. Yeah, you do. Again, that's more about the dark photon and less about the strong dynamics. But yes, I mean, in principle, you could have other types of theory which couple to dark photons. They don't have to be strongly interacting like this. But, yes.
And you do have the dark matter set interactions.
Mm-hmm.
But if you're giving out for that structure formation is a bit tricky.
That's true. That's true. Yes, that's going to place a constraint on the model for sure. But yes, you're completely right.
Okay, any more questions? Let me check also on Zoom if there is.
No,
There's no question. Yeah, I also don't see any questions. So, okay. So then if there are no more questions, we can thank our speaker again.